All right, so Bohr's theory really talked about energy levels, but it didn't thoroughly explain the wave-like behavior of an electron. And so today, more and more has been studied about this, and so we actually use the principles called quantum mechanics, which applies to subatomic particles. And so Bohr's theory is not exactly right, although it's a very good explanation of a lot of it. All right, so de Broglie was someone who kind of took the idea of quantum theory, or the idea of the duality of light, and came up with a relationship called the de Broglie relation. He's the one that said if light acts like a particle, perhaps all particles act like waves then. And so he's saying any particle should have this same duality as light, that everything works as a wave or as a particle. And so he actually rearranged some equations, which we'll see on the next slide. So he said any particle that has mass and velocity should have a wavelength associated with it. He took this equation that light acts like a wave, E equals h nu, and then he also took this equation, E equals mc squared, that talked about light acting like a particle because it's got speed and mass, and then putting them together equal to each other, rearranging them since frequency equals the speed of light over lambda, plugging that in for frequency, we get this equation, mc squared equals hc over lambda. Rearrange it and we get wavelength equals h divided by mc. So in other words, the wavelength should be directly or indirectly related to the mass of a particle. H is a constant and c is a constant. And since c is just the velocity of light, we can rearrange that to just say wavelength. If we're not talking about light specifically, wavelength should equal h over the mass times the velocity. So if something's moving through air and it has a certain velocity, it should have a wavelength associated with it. So this is called de Broglie's relation. Again, it means any particle that has mass should also have a wavelength. Now, he proposed this. So then you might say, well, if all matter has wave properties, why aren't they observed? Well, let's just use his equation to talk about a baseball moving at about 60 miles per hour. So a baseball weighs about 0.145 kilograms, and if it moves about 60 miles per hour, it's really moving 27 meters per second. And if you calculate the wavelength involved with that, you get 1.7 times 10 to the minus 34 meters. Well, this is such a tiny, tiny, tiny size that it's just not observable by anything that we have to detect it. So we don't know if this relationship is true, but it's interesting to think about. Here's just sort of going on about what I was saying. So electrons have wavelengths in the order of 10 to the minus 12th meters. So they're already so tiny. Now, those electrons actually, so they have wave character, and so we should be able to see the particle observed with them. And in fact, this is the basis of the X-ray. They used X-rays to diffract a crystal, and so if they have this particle wave duality, they hit the crystal and they were able to be detected and be collected. Anyway, all of this led to the first electron microscope. And so this duality, I don't know if we could even detect things smaller than that, but it is interesting that it's that they've used it at this level. All right, so the rest of what we're going to talk about in this slideshow is quantum mechanics. And so quantum mechanics is the branch of physics that describes wave properties of these microscopic particles. And so, up until this came along, physics explained a lot of the macroscopic things, but everything got blown out the window when the microscopic came along. Anyway, it's not exactly like Bohr proposed, although I think that's a really helpful picture. We can't we can no longer think of an electron as having a precise orbit in an atom. Quantum mechanics says that if we wanted to know, so electrons aren't orbiting the way you would think of the Earth orbiting the sun. Electrons are kind of moving all over the place, and so we can't actually, in order to describe it as an orbit, we would have to know its exact position and its momentum, or in other words, its velocity, how fast it's going. Heisenberg is someone who, using some calculus and some higher math, showed that it was impossible to know both the exact position and the velocity of an electron at any one time. This is called Heisenberg's uncertainty principle. And you see delta X means that there's some uncertainty in the location of the atom or the electron. And the M delta V is talking about the uncertainty of how fast that particle is moving. And according to his equation, the product of those two has to be greater than or equal to h over 4 pi. This is a bit beyond our class, so you don't need to worry about it. But the main thing is that the better you know delta x, the closer you know the exact location of x, the harder it is for you to know the velocity, or the closer you know the velocity, the harder it is to know where it's located. So that's called Heisenberg's uncertainty principle. So electrons are not, you can't pin them down too well. Okay, this is sort of what I was just saying, that if you rearrange the equation, so we've got delta x, trying to find the location, delta v, the difference in velocity, trying to get close to velocity. Again, as if m gets bigger, the term on the right gets really, really tiny, so the uncertainties are small, and so you can't really use this for bigger particles. However, for electrons that have very small masses, the delta x and the delta v can be described, but we're really not going to worry about that too much in this class. Okay, so again, we can't precisely define an electron's orbit, but we can get, and this is again some higher math, so we're not going to get too deep into it, but we can find the probability of where that electron is at any given moment around the nucleus. Schrodinger was someone who defined this probability in a mathematical expression that he called the wave function. So again, it uses some complex calculus, but it's basically saying, all right, let's find the 99% probability where that electron can be located, and then they solve it, and it turns out to it's a mathematical equation that gives a region in space where this electron can likely be found. And so we'll see some of those shapes in a second. Okay, so according to quantum mechanics, each electron is described by 4 quantum numbers. Every electron is given a series of 4 quantum numbers. The principal quantum number, which is n. And by the way, I'm going to go through these rules, and I think if you bear with me at the end, in a couple of slides, we'll go through some examples, and it hopefully will make a little more sense to you. And then actually in chapter 8, we use these to define a few other things that you might find a little more familiar. Anyway, principal quantum number n. The angular momentum quantum number is a cursive L. The magnetic quantum number is m sub L, and then the spin quantum number m sub S. So every electron has 4 quantum numbers that designate where that electron is located in the atom. It's sort of like, if you know these 4 quantum numbers, you know the address of the electron. You know where it is in the atom. So it's similar to, if you wanted to find where your friend lived, if you knew the state and the city and the street and the house, you would know where that person was. And so this is sort of the same idea. If you're knowing these quantum numbers, you can figure out where the electron is located. Okay, so the principal quantum number, n, represents the shell number in which the electron lives or resides. N can be any positive number greater than 1, or any positive integer greater than 1. So n can be 1, 2, 3, 4, 5, 6, 7. The smaller n is, the smaller the orbital is, the smaller, the closer into the nucleus it is, the smaller it is. And then also the smaller n is, the lower the energy of the electron. So if n equals 1, it's in the first shell. If n equals 2, it's in the second shell. If n equals 3, it's in the third shell. If n equals 4, it's in the fourth shell. Just a little note, sometimes capital letters are used to indicate which shell the electron is in. Your book uses that. I generally don't, but if you come across a problem in OWL or when reading, just note that this is true. So sometimes the first shell is called the K shell, and the second shell is the L, and the third shell is the M, and the fourth shell is the N, just to confuse you even more. Okay, the second quantum number distinguishes subshells within the shell. So you've got a shell, and then within the shell are subshells. You can sort of think of like what I was saying earlier, like the main quantum number, the shell, is sort of like if you think of the state. And then the subshells maybe are like the cities within the state. So these are the different places within the shell that electrons can reside. Okay, now, one thing to keep in mind is that if I'm in the first shell, okay, so within each shell there are n subshells. Whatever shell you're in, that's how many subshells you have. So for example, if you're in the first shell, you have one subshell. If you're in the second shell, there are 2 subshells. If you're in the third shell, you have 3 subshells, and so forth. We can talk about the value of this quantum number, and the quantum number has rules, and L can have any integer value from 0 up to n minus 1. So what does that mean? If n equals 1, then L can only equal 0 because n minus 1 is 0. If L equals 2, if n equals 2, then L can be 0 or 1. If n equals 3, L can be 0, 1, or 2, etc. Okay, these subshells are given letters. So if L equals, here we go, if L equals 0, we call that the S subshell. If L equals 1, we call that the P subshell. If L equals 2, it's the D. If L equals 3, it's F. And if L equals 4, it's G, and so on. 5 would be H, and so forth. Okay, the third quantum number is called the magnetic quantum number, and it'll distinguish how many orbitals are in a given subshell. And each of these, we'll see, have different shapes. But so it's sort of like we've drilled down. We had our state and we have our city, and now this third magnetic quantum number, or this third quantum number, might tell us what the streets are in the city. So each subshell is divided into orbitals, and each orbital can hold 2 electrons. M sub L can have these particular values. They can equal anything from negative L up to positive L, any integer from negative L to positive L. So this means there are 2L plus 1 orbitals, because, so like for example, if L equals 2, then M sub L could be equal to negative 2, negative 1, 0, 1, or 2. So there's 5 different possibilities. If L equals 1, then M sub L could be negative 1, 0, or 1. So 3 possibilities. So if you plug the value for L in, so if I plug 2 in for L, then I have 5 orbitals. Negative 2, negative 1, 0, 1, and 2. If I plug 1 in for L, I have 3 possibilities. Again, negative 1, 0, and 1. If L equals 0, then I only have 1 possibility. That would be 0. If L equals 3, then I have 7 possibilities. That would be -3, -2, -1, 0, 1, 2, 3. And also just keep in mind, well, we're going to summarize this again, but remember if L equals 1, that's a p subshell. So there are 3 orbitals in a p subshell. If L equals 2, that's a d subshell. There are 5 orbitals in a d subshell. If L equals 0, that's a s subshell, and there's 1 orbital in that subshell. Okay, and then finally we have the spin quantum number. It refers to 2 possible spin orientations of the electron. So since any orbital can hold 2 electrons, these values are the spin. They could be either, there's only 2 values, +1/2 and -1/2. So a spin could be either +1/2 or -1/2, and those are the 2 electrons that can reside in a subshell. So this is a little summary. So again, if n equals 1, then I only have 1 possibility for L, which is 0. And if L equals 0, I only have 1 possibility for m sub L, which is also 0. And that we designate that as a 1s subshell, and there's just 1 of them. Okay, if n equals 2, I have 2 possible subshells. L could either be 0 or 1, because L could be any integer up to n minus 1. So L could be 0 or 1. Well, 0 corresponds to a 2s subshell, and 1 corresponds to a p subshell. So if it's a 2 and a 1, it's a 2p subshell. Now look at the m sub L's. For if n equals 2 and L equals 0, the only possibility for m sub L is 0. And so there is 1 orbital in the s subshell, in the 2s subshell. Now, if L equals 1, there's 3 possibilities, -1, 0, and +1. So there are 3 orbitals in a 2p subshell. Now, if you go to the third shell, again, we have 3 subshells because we're in the third shell. So the L values can be either 0, 1, or 2, indicating an SP or D subshell. And then you can see that they start to repeat themselves. If it's an S subshell, again, there's only 1 possibility, m sub L equal to 0. If you're in a P subshell, there's 3 m sub L values, so 3 orbitals. If you are in the 5th shell, if you're in the D subshell of the 3rd shell, then you have 5 possibilities. So the D subshell has 5 orbitals. And then you can see on the 4th shell, it keeps going. And so you keep layering. And the 4th shell can also have an F subshell, which has 7 orbitals. All right, and this sort of is a little bit of a diagram. So the first shell only has 1 subshell, the 1s, and it only has 1 orbital. The second shell has 2 subshells, 2s and 2p. The 2s's have 1 orbital and the p's have 3 orbitals. The third shell has 3 subshells, s, p, and d, 1 orbital in the s, 3 orbitals in the p, 5 orbitals in the d. And then the 4th shell, you can see, has the 4 subshells, s, p, d, and f, 1, 3, 5, and 7. So again, remember that these are all based on probabilities, molecular, chemical, mathematical equations to represent the probability of where an electron is more likely to be. S subshells, when you solve the mathematical equation, they actually look like a sphere. And P subshells look like dumbbells. And then D subshells, actually there are 5 different ones. Remember, they have different shapes, which we'll see in just a second. Let's look at them. All right, so an S subshell just looks like a sphere centered around the nucleus is in the center of that sphere. And even if it's a 2s is also spherical. It's just bigger, and so it's bigger than the 1s. Okay, and this is just a 3D look at the 2 different orbitals. Just 2s is bigger than 1s. The p orbitals look like dumbbells, and so there's 3 of them, and they look identical. They're just located in different directions. So if you put all 3 of them together, you would have one on the x-axis, one on the y-axis, and one on the z-axis. But again, you can sort of see with the dots that it's showing the probability. And then these are the 5d orbitals, and you can see that 4 out of the 5 of them look like clover leaves in different directions, and then the 5th one sort of looks like a, I don't know, a dumbbell with a donut around it. But again, these are probabilities where the electrons are most likely to be located. So I think it will help to summarize, review the quantum numbers. N is the main shell, so 1, 2, 3, 4, 5. So then L indicates the subshell. If L equals the value of 0, we know we're talking about an S subshell. If L equals the value 1, we're in a P subshell. If L equals 2, we're in a D subshell. There can be N subshells in any shell. So if N equals 1, there's one subshell, and that's the 1s. If N equals 2, there are 2 possible subshells, 2s and 2p. If N equals 3, there are 3 subshells, 3s, 3p, and 3d. So M sub L indicates how many orbitals there are in each subshell. So let's take it a step further. Like say we're talking about the state of Virginia. So if we're talking about the city. So if we're talking about city 1, it could be Abingdon. City 2 could be Bristol. City 3 could be Marion. And then L is the subshell. So we could say, well, in city 1, there's only one street. It's S Street. In city 2, there's 2 streets, S and P Street. In city 3, there's 3 streets, S, P, and D Street. And then M sub L is how many orbitals there are in each subshell, so we could sort of think of them as houses. So on an S street, there can only be one house, or there's only one orbital. On a P subshell, there are 3 orbitals, or you could think of P Street having 3 houses. On any D subshell, there's 5 orbitals. On any F subshell, there's 7. So again, if you're on S Street, there's 1 house. On P Street, there's 3 houses. On D Street, there's 5 houses, etc. City 1 only has 1 street with 1 house. City 2, though, has 2 streets, and on the first street, it has 1 house in the S Street, and on P Street it has 3 houses. So you can see it builds up from there. And then M sub S indicates the spin, and spin could be either plus 1/2 or minus 1/2. That could be like how many people. There could be only 2 people in any house. If you kind of think about it like that. All right, just some other things that are helpful to know. The total number of subshells in a shell is equal to N. So if if you're on the second shell, there are 2 subshells. If you're on the third shell, there's 3 subshells. The total number of orbitals equals N squared. If you're on the second shell, there are 4 orbitals, 1s and 3 p's. If you're on this third shell, there's 9 orbitals, 1s, 3p, and 5d, etc. The total number of electrons then is twice that. So if you have 9 orbitals on the third shell, then you have 18 electrons. If you have 4 orbitals on the second shell, you have 8 electrons. If you're on the fourth shell, then you have 16 orbitals, 1s, 3p, 5d, and 7f. So that means you have twice that, or 32 electrons. Okay, so let's do some examples. What kind of subshell do we have if N equals 5 and L equals 4? Well, we're on the 5th shell, so it's 5, whatever. And if you remember, if you go back, S equals 0, 1 equals P, 2 equals D, 3 equals F, so 4 equals G. So this would be a 5G subshell. How many orbitals and electrons are there in this subshell? Well, if we're in the 4th subshell, then we should have 2 times 4, 8 plus 1, so 9 orbitals and 18 electrons. So that's just in the subshell. All right, what do these set of quantum numbers indicate? Well, if N equals 4, that means we're on the 4th shell. If L equals 2, that means we're in the 4D subshell. If M sub L equals -2, we're in the first out of the 5 orbitals, or the -2 orbital out of the 5 possible orbitals on that subshell. And m sub l plus 1/2 means we have it's a positive spin. So it's the -2 orbital of the 4d subshell and has a positive spin. Again, if you think of the orbitals as houses, it would be like the house named -2, and then there's a house named -1, and a house named 0, and a house named 1, and a house named 2. It can get a little confusing, but what kind of subshell is it if n equals 6 and L equals 1? Okay, so if it's in the 6th shell and L equals 1, that's a p subshell, so that would be the 6p subshell. All right, why are the following sets of quantum numbers not permissible? Well, if n equals 3, little l can equal 0, 1, or 2, so that's fine. M sub l can equal -L up to positive L, so it can only equal -2, -1, 0, 1, or 2. So M sub l cannot be equal to 3. M sub s is fine at -1/2. For the second one, n equals 2, and L can equal 1, because L can be anything up to n minus 1. And M sub L can be -1, because M sub L could be -1, 0, or 1. M sub S cannot be 3/2. It can only be +1/2 or -1/2. And then for the third one, n cannot equal 0. It has to start with 1. What are the set of quantum numbers for an electron in the 3s orbital with a negative spin? Okay, well, if it's in the 3s orbital, it would be, let's see, it would be in the n would equal 3, L would equal 0 because that's a s subshell. Since L equals 0, M sub L can only equal 0, and then a negative spin would be -1/2. All right, so what should you be able to do at the end of this chapter? You should be able to find wavelength from frequency or frequency from wavelength. You should be able to calculate the energy of a photon using E equals h nu. You should be able to determine the wavelength or frequency of any hydrogen atom transition. You should be able to, well, don't worry about the de Broglie relationship. Using the rules of quantum numbers that we just went over, you should be able to identify any electron